part 1 was into This is the 13th lecture. We shall continue the discussion on that problem in one of the tutorial classes. 13th lecture, today is 7th February, and we discuss natural response of second order circuit, and if time permits then we shall discuss these two terms, poles and zeros. You remember in the second order circuit that we had considered, what we had considered was we have a capacitance which is charged to a voltage of capital V, let's say V0, and then at t equal to 0 is connected across an inductance L and a resistance R. The current that flows in the circuit is I. We are considering this particular LCR circuit. The initial condition is that Vc0 minus is V0, and then naturally as time increases, small I at t equal to 0, that is when the capacitor is switched to this series combination, the current would be 0, and then the current would gradually increase and then decrease. After infinite amount of time it would decrease. Qualitatively this is the phenomenon, but depending on the relative values of R, C and L, the way it does so would be quite different, and we have discussed one of the cases, but before that let me write the differential equation. Differential equation was L d2i dt2 plus R di dt plus I by C equal to 0. How did we obtain this equation? We first obtained an integro differential equation, that is Ri plus L di dt plus 1 by C integral I dt V0 minus that, and then we differentiated this to obtain a homogeneous differential equation, that is the right hand side is equal to 0, and then we argued that the solution to this equation shall be, we can try a solution of the form e to the st, some constant multiplied by this, and with this we ended up in a quadratic equation, that is small s satisfies a quadratic equation of the form s squared plus s r by L plus 1 over LC equal to 0. If you substitute this in this equation and clear both sides of a e to the st, then this is the equation that you get, which clearly has two solutions, and the two solutions are S12 is equal to minus r by 2l plus minus square root of r by 2l whole squared minus 1 over LC. And if you denote the quantity under the square root sign as capital D, then you know the capital D stands for discriminant, and we had considered the case when discriminant is greater than 0. This leads to S1 not equal to S2, and both S1 and S2 are real and negative, and therefore the general solution to the current function would be A1 e to the S1t plus A2 e to the S2t. And we had taken a specific example to show how the current varies with time. The general solution, we had evaluated A1 and A2 from the initial conditions, and there were two initial conditions to bother about. One of them was that I of 0 was equal to 0, I of 0 was equal to 0, and the other initial condition was that di dt at 0 plus is equal to V0 by L. These are the two initial conditions. These initial conditions will apply to every situation whether capital D is greater than 0, whether capital D is equal to 0 or less than 0, it does not matter. It satisfies, these initial conditions apply to all conditions, all parameter conditions, that is values of R, L and C, and with this, under the condition that D greater than 0, we had shown that the total solution to the current is given by V0 L S1 minus S2 e to the S1t minus e to the S2t. And we had taken a special case and showed that the plot of the current would look like this, that it would show a maximum and then it would fall exponentially with time. Okay, this is one case. Now let's consider the other case in which D is less than 0. Then we shall consider the juncture case, namely D is equal to 0, that is the transition from D greater than 0 to D less than 0, or the other way around. We shall consider the transition case at the last instance. Alright, first let us consider, we have considered capital D greater than 0, let us consider capital D less than 0. Then S1, 2, the two roots are minus R by 2L plus minus square root of D is less than 0, that is R squared by 4L squared is less than 1 over LC, and therefore this quantity is negative. I can write this as minus R by 2L plus minus square root of, I can take a minus 1 common here and then write a positive quantity 1 by LC minus R squared by 4L squared, and square root of minus 1 is J, minus R by 2L plus minus J. In mathematics one writes an I, but small I we use for current in electrical engineering, and therefore in electrical engineering we always use a J as square root of minus 1. So J square root of 1 over LC minus R squared by 4L squared, this would be the nature of the roots. And you see that unless capital R is 0, the roots are in general complex quantities. This is a real quantity and this is a complex quantity. Let us consider, let us call the real quantity as minus alpha, that is minus R by 2L, and plus minus J, let us call this quantity as omega 0, and omega 0 is a positive quantity. We have taken plus minus here. So the roots are in general complex, minus alpha plus minus J omega 0, and any complex quantity can be represented in the complex plane, where it is a two-dimensional plane, rectangular coordinates. Along the x-axis we represent the real part, along the y-axis we represent the imaginary part, and therefore that plane, that complex plane, we shall denote as the S plane. As you see, these values are values of S. We had, what is S? S was the power of the exponent divided by t. So these are the values of S. S1, 2 are also the roots of the characteristic equation, roots of the characteristic equation, and these roots can be represented on the so-called Argand diagram. If you are not acquainted with the name, it doesn't matter, but what we do is the real part of S, we consider an S plane. The real part of S is represented on the x-axis and we call it the sigma axis, and the imaginary part of S is represented on the y-axis, the orthogonal axis, and we call the omega axis or the j omega axis. This is the usual convention for electrical engineers, that we show the imaginary value explicitly, sigma plus j omega. For example, this is the 0, 0 point. So our S in general therefore is sigma plus j omega. Now if we have, let's say, minus 1 plus minus plus j2, then we shall go minus 1 in this direction and we go 2 units perpendicular to it in the upward direction, and our point would be somewhere here. Now in our case, the roots are S12 is equal to minus alpha plus minus j omega 0. So what we do is we go minus alpha to the left. Let's say this is the point minus alpha. Then we go up and down by a distance of omega 0. So we have one of the roots here, and we show this by a circle where this distance is j omega 0, and we go down by the same distance and put a circle here. This distance is minus j omega 0. So these 2 points painted green inside are the 2 roots of the characteristic equation, and they can be represented in the complex plane. This plane is called a complex plane because we are representing complex quantities on this plane, or the S plane. This circuit, an RLC series circuit, RLC, in which Vc 0 minus is equal to some voltage V0. The current in the circuit, if this is the direction of the current, I of 0 minus is equal to 0, and by continuity of capacitor voltage and inductor current, we know that this should be true. The other initial condition is that L di dt at t equal to 0 plus should be equal to V0. And with these initial conditions, we have solved the circuit for the case when d, the discriminant, is greater than 0. If you recall, the characteristic equation of this circuit, characteristic equation was s squared plus, yes, r by L s plus 1 over LC equal to 0, which has 2 roots, S12 equal to minus r by 2L plus minus square root of r by 2L whole squared minus 1 over LC, and it is this quantity under the square root sign which we have called capital D. For d greater than 0, we saw that the roots are real, distinct and negative, and we saw that the complete solution could be worked out in terms of the initial conditions as, if you recall, d greater than 0, the current was given by V0 by L S1 minus S2 e to the S1t minus e to the S2t. Is that correct? I hope that is correct, yes. And we are trying to see what happens if d is less than 0. We argued that if d is less than 0, then S12 can be written as minus alpha plus minus j omega 0, where alpha is equal to r by 2L and omega 0 squared is equal to 1 over LC minus r by 2L whole squared. And as you can see, r by 2L is simply alpha, so I can write omega 0 squared as minus alpha squared, and this quantity 1 by LC, let us use another symbol, that is omega n squared. Let us use omega n squared as 1 by LC. Then you notice that omega n is simply equal to omega 0 when alpha equals 0. That means if there is no resistance in the circuit, then omega 0 is simply equal to omega n. If there is no resistance in the circuit, where are the roots of the characteristic equation? They are purely imaginary, plus minus j square root of 1 by LC, which means that the roots shall be plus minus j omega n, and therefore omega n has a physical significance. Now under this condition that d is less than 0, we showed last time that the current solution shall be of the form A1 e to the power minus alpha plus j omega 0 t plus A2 e to the power minus alpha minus j omega 0 t. And we argued that if I take e to the minus alpha t out, e to the minus alpha t out, then the rest of the quantity inside the brackets could be put in terms of cosine and sine, and the cosine and sine could then be combined into this particular form, sine of omega 0 t plus a theta, where you see the initial constants. I did these steps last time. Okay. Now you see the initial constants a1 and a2 have now been replaced by modified constants c and theta, which have to be evaluated from the initial conditions. Let's look at the initial conditions. I of 0 plus is equal to 0. This means if I put t equal to 0 here, then you see c sine theta should be equal to 0, which means that theta should be equal to 0. Alright, and therefore my solution is I of t is equal to c e to the minus alpha t sine of omega 0 t. Once again we know that L di dt, the other equation is that L di dt at t equal to 0 plus is equal to V0. If I substitute I of t equal to this here and put t equal to 0, then what do you think I will get? I will simply get L times, I should use some other constant here. I shouldn't use a C. Why? C I have used for capacitance. So let's use a C1, alright? Let's use a C1. Then if I do this, if I substitute here the differentiation and put t equal to 0, can I skip the algebra and write simply that C1 will be equal to V0 divided by L. That's what it shall be. Alright? Which means, isn't this okay? If you want me to do the algebra, I will gladly do it. There is no problem.
So it will be divided by L omega.
Okay. I am glad you caught that. This will be V0 divided by L omega naught. That is correct. Because a differentiation of this shall bring omega 0. Alright. So C omega 0 cosine omega 0 t multiplied by e to the minus LT alpha t. Put t equal to 0, this omega 0 shall be there. Thank you very much. Okay. And therefore my current solution would be, total solution is V0 by L omega 0 sine of omega 0 t times e to the minus alpha t. That factor shall be there. Alright. Now suppose sine of omega 0 t was not there. If this was not there, then you see dependence on time is exponentially decaying, because alpha is capital R. If you recall, alpha is capital R divided by 2L. It's a positive quantity, and therefore e to the minus alpha t decays with time. The presence of sine omega 0 t means that it is the product of an exponentially decaying curve and a sine curve. Therefore, what it means is that if I plot I of t versus t, the envelope of the curve shall exponentially decay, whereas inside there shall be a sinusoid. If alpha was 0, if this was not there, then it would be a non-decaying sinusoid. On the other hand, if alpha t is there, as time increases, naturally the amplitude of the sine wave gradually decreases. It decreases exponentially, and therefore the figure that I shall get, it shall start from here. The figure that I shall get would be like this. It shall start from here, and then gradually the sine wave, as time proceeds, the maxima and minima shall gradually decrease. It is not exactly a periodic wave, because after one period it does not repeat. The amplitude goes down. So this is a decaying decaying sinusoid. How does it decay? The rule for decay is exponential. So exponentially decaying sinusoid. It is as if the sinusoid is being damped with time. It is as if the sinusoid is damped with time, and therefore this situation is called damped oscillation. Okay, there is an oscillation, but the oscillation amplitude gradually decays, so it's a damped oscillation. Now if alpha was equal to 0, then you see the oscillations would have been undamped, that is, the amplitude would have remained constant whatever the time is, and therefore you now get a physical significance of the quantity omega 0. Omega 0 is obviously the damped frequency of oscillation, or frequency of oscillation under the damped condition, and you see omega n then is the frequency of oscillation under undamped condition, and omega n therefore is called the natural frequency of oscillation. Natural frequency of oscillation, that is, if the damping was equal to 0, then the oscillation, well, undamped natural frequency of oscillation. The word natural comes because it is not a forced oscillation. It is an oscillation because of the initial energy in the system. The system has been left alone, and therefore it shows its natural behavior. So omega n has the interpretation of undamped natural frequency of oscillation, and omega 0 is the damped natural frequency of oscillation. Alright, damped natural frequency of oscillation, and alpha is the damping coefficient. Alpha is the damping coefficient. What is the unit of alpha? 1 over t, that is correct. And you know that omega 0 squared is omega n squared minus alpha squared. Alright, so all the three quantities, omega 0, omega n and alpha, they have a physical significance, and this is the significance. The envelope decays according to, this is V0 by L omega 0 e to the power minus alpha t. We can take an example at this point. This is the general solution. We can take an example. The condition is that r squared by 4l squared should be less than 1 by LC. This is the condition under which oscillations take place, and the oscillations shall be damped oscillations. Now there are various combinations of R, L and C which satisfy this, but one of them, let's say C is 117 farad. We have taken a peculiar value so as to get nice numbers, and capital R equal to, let's say, 2 ohms. Then the roots are S12 is equal to, you can see, minus R by 2L, so minus 1 plus minus, now R squared by 4L squared is given by 4, and 1 by LC is 17. R squared by 4L squared is 1, that's right. So 1 definitely is less than 17, and you therefore see that the roots are complex, and 17 minus 1 is 16, square root of 16 is 4, so minus 1 plus minus j4. And since we have found out the general solution already, we can write down the current solution as, what will be the constant? V0 divided by L omega 0. L is 1 Henry. What is omega 0? 4. And therefore V0 by 4 e to the power minus, what is alpha? 1. So it is minus t. No, alpha is 1. The roots are minus alpha plus minus j omega 0. Alright. So alpha is equal to 1. Then sine of, yes, 4t. This is the solution. Alright, if you know the general solution for any given combination, you can always find this out. Now we have considered two cases, that is capital D greater than 0. In this case there are no oscillations. The solution consists of the sum of two exponentials, e to the minus s1t and e to the minus s2t, where s1 and s2 are both real and negative. Alright, e to the s1t minus e to the s2t, a1 plus a2. This is the solution, where s1 and s2 are both negative, there are no oscillations, so the current starts from 0, attains a maximum and then goes to 0. On the other hand, if D is less than 0, then we have oscillations. We have V0 by L omega 0 e to the minus alpha t sine of omega 0 t. Alright. The borderline between these two, or the transition case, which happens at D equal to 0, occurs obviously when R squared by 4L squared is equal to 1 over LC. Alright, this is a very special condition, and the condition on the resistance R to satisfy this is called R critical. It is a critical value of resistance for which this shall be true. Alright, if this equality becomes an inequality, there shall be either oscillations or no oscillations, and therefore this is a critical case, and this case is called the case of critical damping. Critical damping, that is, if the damping is slightly less, then there shall be what? There shall be oscillations. If the damping is slightly less, there shall be oscillations. Alpha is the damping coefficient. If the damping is slightly more, there shall be no oscillations, and therefore this case D greater than 0 is called an overdamped case. Overdamped means no oscillations in the natural response, and naturally D less than 0 should be called an underdamped case. Alright, underdamped case, and D equal to 0 is the so called critical damping case. Critical damping. It determines the boundary between oscillations and no oscillations.